go ahead and get started. I'm Joe Medeiros, and I'm happy to introduce our speaker today. I'm with Sierra College Press, and we've been doing these great and fun intellectual salons on time last semester and this, looking at this nebular, difficult to pin down concept of time. Is it a real thing? Is it a human construct? Well, it's kind of both, isn't it? It's a little nebular, kind of floats around there, but we certainly need it. I mean, you know, every time you want to go on a plane flight, or if you want your employees to show up on time or whatever, we're always looking at time. So this has really been a lot of fun. And it's joint, the event is a cooperative effort between Sierra College Library, Sierra College Press, and the Friends of the Library. So we're trying to open up the library for a little bit more engagement, and we're happy to invite anybody to sit down and enjoy the salon for the day. So welcome to you all. If any of you are interested in Flex Credit, I'm going to put this. Does anybody like to grab this right now? There you go. This lady has it right here. So let me introduce, let's get rolling. Dick has done a phenomenal job of putting three-dimensional things together to illustrate his concept and his program today. And it's a real pleasure to introduce Dick Morasso, who comes to us from lots of years of work in the community college system. He actually started at a community college. As a matter of fact, he started at the first community college in the United States, Joliet. There's a Joliet.
You like to pronounce it.
I know. If it's Joliet if you're at the college, it's like Joliet if you're at the prison, and so on. So actually moved from Joliet to Folsom, California. So I wonder about this prison focus of his. He likes parameters. So. He moved out west to go to San Diego State University, where he took his bachelor's degree in mathematics, and then, I don't know if this is a logical movement, then to get his master's of science degree in astronomy at San Diego State. He taught at Grossmont, or actually did some student teaching. Did you teach at Grossmont? Grossmont, what is that? Large mountain? That's why he always wanted to come into the Sierra Nevada to get the biggest mountains of the West. And then taught at Southwestern University, where he was department chair and the first director of their planetarium there. And he came to Sierra College in the mid-'70s, and he taught here until the year 2000. He was chairman of the astronomy department and kept the planetarium, got it rolling, and got distant observational facilities going at Blue Canyon, and I see people here still involved in that, and up at Grass Valley, our Nevada County campus as well. So he's always looking up, always looking for things to do. Dick retired in 2000, but then taught part-time until just a few years ago, I think, and he's too busy making stuff. He works with the Friends of the Library, and has helped build so many things here in the library. He's a member of the board of directors, the museum committee, as well as the Sierra College Foundation. As a matter of fact, you rode your bike all the way across the United States, right? As in a fundraiser.
I did that
for the foundation. Yeah. Always helping out Sierra College, and it's a great pleasure for me to introduce Dick, who apparently just recently has made his 75th trip all the way around the sun. And about to? Oh, okay, okay. So I asked Dick, can I have a subtitle for today's topic? And he says, "Why a Clock Goes Tick-Tock and Finding Your Way Home." And in summary, a historical sketch of horology. Maybe you can discuss that just a little bit.
Talk about that.
You better define that. And how celestial observations compete with machines.
Yeah,
and so you're
good,
starting now. No.
Yeah, okay.
Welcome to Dick.
Thank you.
There you go.
I'm going to turn this over. It's an hour.
There we go.
Okay. All right.
He's got a real hourglass there.
Yeah,
Put this right here and drop that in your pocket, and
Okay.
we're on our way.
How's that sound? Good. Hello, everyone. Thank you, Joe, for that introduction. And I have to, in the interest of full disclosure, I have to say something about this title here. All right. I stole it off a book. It's the Longitude Prize. Very good book, very easy to read, by Joan Dash. And I'm not sure they have it in this library, but I'd be happy to loan it to anybody who wants to see it. So there's that. And secondly, there's also another Longitude Prize that Joe pointed out to me regarding microbiology or microbial studies. And so they must be dealing with really little teeny tiny clocks, right? And so that would be my guess on that. But anyway, thanks for coming today. We all appreciate it. And what I'd like to start off with first is what we're going to do. Why are we here? And one thing is that, how many of you have taken a cruise? Okay. Now, once you're on that ship, you ask yourself, where am I? You're out in the middle of the ocean. Where am I? Question, well, I'm in the bar, or I'm at the pool, or I'm in my room. But the bigger question is, where's the ship located? And in terms of its position relative to where you left. So that's a question you know that the captain has well in hand. At least you hope that he or she does. So we're going to talk a little bit about this, but we're going to go back in time. We're going to start by going back 50 years. And I picked that time because that's when I first walked into a classroom. And in my first 2 weeks at Southwestern College, a student walked into my class, and she had under one arm a globe. Not this big, but similar to this in shape. And she had in her other hand a shot glass. So I thought, well, it's kind of early in the day to party, and what would you do with a globe? But she came into the classroom, and it was like probably mid to late September after we got rolling. And she said, I want to show the class something. It was just to me, it was so intriguing that a student would walk in early in the semester and say, I want to show the class something. So she took the globe, took the whole class outside, set the globe up so that, she said, you have to set it up a certain way. Set it up so that, well, then it was San Diego, Chula Vista, San Diego, just about the same thing. Just so that it's at the top of the globe. So if you found San Diego, you'd put your finger on it, and your finger would be at the top of the globe. Then she took, this was in the afternoon, it's probably about 2 o'clock as I recall. I remember this. I don't know why I remember things like that. And she put the shot glass on the globe like that and moved it around until the image at the bottom of the shot glass, if it's a good shot glass, you know, this is a test of a good shot glass, will form a little lens, or the lens will form a little image of the sun right under it. And you move it around till the image is right in the center of the shot glass, and she says, Shazam! That's where the sun is directly overhead on the earth right now. And that led to a discussion. The discussion was, where could it ever be? In other words, can it be up here? Can it be over here? Depends on the time of day, time of year. Can it ever be anywhere else? And of course, she knew the answer. It cannot be anywhere above the Tropic of, what's the northern one called? Cancer. And the sun cannot appear any further south than the Tropic of Capricorn. Named after two constellations, Cancer and Capricorn, which were really the constellations the sun occupied in those days about 2,000 years ago. Which lets me do this now. Go back more than 2,000 years, about 2,200 years. To this time, Brian, did the Greeks have that big a head? Oh, he did. But Eratosthenes did something that was really quite remarkable, because 200 years prior to that would have been Pythagoras. Pythagoras taught the fact that the earth was round. Okay? He had some suppositions. Suppose it was because the earth cast a shadow on the moon during a lunar eclipse. The shadow was curved, and if it's a sphere, it would be a curved shape. It would remain constant, and it couldn't be a flat object on a curved surface. It had to be a curved object, as it was. And he drew a bunch of conclusions based on observation of the moon, the fact that it was round, and other things that they would observe to see that. He was able to do the same thing. He didn't use a shot glass, but he was able to realize that in the town of Syene, which is Aswan now, that this shot glass on a particular day of the year, the first day of summer, which one is that? June 21st, okay? On that day, if we go around the world here, to northern Africa, Egypt. I'll find it. Did I pass it? Okay, there we go. And so up here, he found that located in the town of Alexandria, he knew on a particular day, because he was able to observe that year after year, that on a particular day, one day of the year, on June 21st, that the sun at the town of Syene or Aswan would shine straight down a well. He knew that. He didn't have to be there because he knew it was going to happen. But he observed the sun in Alexandria, and it wasn't straight overhead. It differed by an amount that happened to be right around 7 degrees. That's this angle right here. I guess I could use this fancy pointer. Right in there, that angle. He surmised that that angle right here is the same as this angle, which happened to be 7 degrees, as I said. He realized that as you traveled from Syene to Alexandria, you went through 7 degrees of latitude, but how far did you go on the surface of the Earth? It was intriguing the way he got that answer. One theory is they had somebody pace it off. When he got done, it was so many stadia, because back then, a stadia, they think, was about 600 feet, because it was the length of a stadium. Okay? And he figured out how many stadia it was, or he used a camel. Some other people, some other historians suggest the camel walked a certain distance a day. And it took so many days to go from Alexandria to Syene. And he deduced it from that. He came out with about 500 miles. Well, think of that. 500 miles from Alexandria to the well, where the sun at that moment was shining straight down the well. 500 miles represents 7 degrees of the Earth. So how do you figure out the whole circumference? You take 7 degrees is to 360, as 500 miles is to the whole thing. And he was able to come up with, this is questionable. It could be 25,000 plus or minus 1,000 miles. But the real published value from pole to pole, and back to the same pole again, is 24,859. He was pretty close. Very close. Remarkably close. Suspiciously close, okay? Now, we go forward. We went from Pythagoras to Eratosthenes. What was that? 200 years. And from Eratosthenes to Ptolemy. Ptolemy was a person who set up all the longitude and had the idea for longitude and latitude, and put all these marks on the globe. That, in a sense, tells us where we are, where we're going. Something happened in that period of time. It's almost 1,700 years before we got to Columbus. 1,700 years. And I was looking at a book just before I started, and Richard Feynman said something about time. He says, time is what's happening when nothing else does. And you think all those periods of time, hundreds or thousands of years go by, where virtually nothing happens. Well, something happens, but nothing we're interested in, okay? Or some people are. But Columbus grossly underestimated the size of the Earth. And I think that was because he was making a pitch to Isabella and Ferdinand. He didn't want to use that 25,000 mile circumference, because what did Columbus want to do? He wanted to go to the East Indies the other way. Like, you always tell yourself, well, I can go to San Francisco by going east. That's the long way, isn't it? Really long way. But he thought, because the Earth wasn't quite as big as Eratosthenes had suggested, he was going to go the other way. He would run into it in that direction. Little did he know that there was something in the way, fortunately for him, because had he gone without North and South America being there, he would have perished. He would have been gone. That would have been all over. He would have starved to death. That globe right there, there's something wrong with that globe. Take a look at it and tell me what it is.
There's a Western Hemisphere.
There is a Western Hemisphere. There should be no Western Hemisphere, because Columbus would be saying here, what's of this? Okay? And right there should be blank. And yet somebody, artistic license, put the globe there with North and South America. And he actually didn't run into North America. He ran into what's now Cuba, or what's now the Dominican Republic, and those islands down there. He didn't get up there. In fact, when he came across the path he took when he left Spain, it kind of dropped south. I guess he was getting cold. dropped south and ran into those islands. Now, he actually hit what is now known as the West Indies. Okay, he didn't get to the East Indies. Then he came back, and Isabella was happy that he found things. He's looking for gold. I have a lower opinion of Columbus now, I'm sorry to say. I used to gripe about not celebrating Columbus Day. I don't care anymore. Okay? He got into things like slave trade and stuff like that. He didn't really hit the bulk of North America. Okay? Also, Amerigo Vespucci. We should have Vespucci Day instead. It's in March, but that's not so bad. All right? Because he actually discovered or understood the significance of what was North and South America. And he realized that the land you bumped into wasn't East Asia. It was a different continent. And that, to me, is a really great discovery. Okay, let's move on here with what we're supposed to be talking about today. The sailors at the time, like Columbus was really given 3 ships, and they were second or third hand. I think Isabella suspected they might crash somewhere, so he gave them ships. And if you got off the elevator today, if you walked off the elevator and got to the circulation desk, you would have walked from the back to the front of the Santa Maria. That's how big it was. Now, if you've been on a cruise ship, they're 1,000 feet long. Santa Maria would probably fit in the pool of some of those cruise ships. And he was able to use very crude instruments. And this one I built to show you. It's called a cross staff. This will move if you force it, okay, back and forth. And this kind of reminds me of a story. These 2 pins right here are 2 inches apart. And a student came up to me once before I started class, even from a prior semester, says, I saw Venus and the moon the other night. It was beautiful. They were 2 inches apart. And you know, I was so impressed that he was able to identify Venus and the moon. I said nothing of the units of measure. Okay? And what did he mean? He meant that if you held your fingers out like that, you could get the moon and Venus in between your 2 fingers. That's perfectly okay. So we use a device that's called a cross staff. You put your eye right about here, and you pick the 2 pins closest to indicating the separation of the object you're looking at in the sky, as this gentleman is doing here. He might be measuring the elevation of the North Star, which gives you an idea of your latitude, because figuring out latitude on the Earth is real easy. This device right here, it's called a quadrant. You can build them in my astronomy classes, and I think they still do it now in astronomy. Anybody here from astronomy class? Oh, okay. Art class? So this device right here is just a bolt, a weight hanging on a string, and as you tilt this up, it actually registers the angle at which you're looking up along the stick, called a quadrant. Real simple device. It's a precursor to the sextant, which doesn't come along till much time later, a couple hundred years later. So they use these simple devices along with this device. Where did it go? Oh, it's over here. The compass. This is a really nice compass. They probably didn't have one this nice right here. And it naturally pointed almost north, because you know that north is not quite true north. And what is that? Why is that? How does a compass work, and what principle?
The south magnetic pole of the compass points to the north magnet.
Yeah, magnetism.
Pole.
The Earth's got a magnetic field. Does the magnetic field line up true north and south?
No.
It doesn't cooperate one bit. In fact, the north pole of the Earth wanders around right now, right here. If we were to let this thing go, here, uncage it, I'll pass this around so you guys can look at it. You push this one button, it frees the compass. And when it points north, it's really pointing about 13 degrees east of true north. Okay? If you really want to know where north is, you go outside at night, you find the North Star, and you look at the North Star and drop a line down to the horizon. That's true north. It's very dependable. So that's how they navigate it. Another way they navigate it is they travel along parallels of latitude. They had no idea of what their longitude was. Very crude estimate of longitude. They would use a device like a chip log. And here's a modern rendition of a chip log. And you throw this in the water behind the boat, all right? and it goes in the water, and once it gets filled with water, it produces a lot of drag, and then it pulls on the string, all right? And then you start a timer when you get to the first, where is it? You get to the first knot, okay? There's a knot in the string, all right? You turn the clock over, and if the knots are like 48 feet apart and the timer is about 28 seconds in duration, you count how many knots go by over the stern, and then when the 28 seconds is up, you say stop. So let's say I'll just let 4 knots go through. Guess what your speed is? 4 knots, okay? And that's where the knots came from. You can convert knots into miles per hour if you figure a knot's about 1.15 miles per hour. And now this seems kind of crude, because it was, but it enabled them to figure out about how far they traveled. It's called dead reckoning. Dead reckoning is starting with an assumed position, knowing your speed and direction, where you're going to be. Dead is an unfortunate term, because a lot of sailors ended up precisely like that. But the word dead really came from DED, for deduced reckoning, DED dot, abbreviated, and it somehow became DEAD. So go figure. Here we see a building that was founded by Charles III. Charles III. And you know, I don't have to remember so much if I look at the slide. But Charles II, and he did this, put the money into it, for the purpose of having the stars and the moon and the planets observed by astronomers so they could get a better idea of where they were on the Earth by using astronomy. This is the whole key. And this is the Greenwich Observatory. You can still go there. It's a great trip if you ever go to London. It's outside of London. You go up there, you can look at the original telescope and also see a device known as a meridian transit. It's a telescope that just goes north and south and precisely determines what time a particular star crosses a line, a meridian. It keeps the time by stars. It's a very precise device, not as precise as the cesium clock, which we aren't even going to talk about today, okay? But it was proposed, the reason is to accumulate astronomical information to improve navigation. That's basically what it was all about. Now, a lot of time has gone by. We had about 1,700 years from Eratosthenes to Columbus. Then we had about another 200 or 300 years to the time of Galileo and Newton and all these great thinkers. And we had a moment in history. This is just a graphic. It doesn't represent the actual event. In 1707, a fleet of British naval ships was coming from, here we go, from Gibraltar, and they were traveling back north to Portsmouth, England, and they had to go through the English Channel. Well, when you're going through the English Channel, you can't go a little too far left or a little too far right, because the ship will run into something. So they had a good grasp on their latitude. Once again, the latitude, you just go out and look at the North Star, in a clear night, or look at the sun's highest position in the sky, determine the latitude, piece of cake. The longitude, how far east and west you are, depends on the clock, depends on what time it is, and comparing that time with Greenwich time. They got up to here, and unfortunately, they ran into the Scilly Islands. 4 ships sank. They lost between 800 and 2,000 men. That was probably one of the most catastrophic events in the British naval history. They may have had other losses during like the First or Second World War, but for a single event, that was it shook the nation. And that's why, well, again, it took 7 years, but they established the Board of Longitude. And this is where the prize comes in. This is where the title of this whole presentation comes in. It's called the Longitude Prize. And again, I guess I should read it. 1714, 7 years after the tragedy, the Act of Parliament offered £20,000 for a solution to the longitude. And it had to be within a half a degree of longitude or 2 minutes of time. If you look on this globe right here, you want to come up later. And by the way, I invite you to come and look at this stuff later. I'll try to end it a little before the regular time. And you'll see that the latitude lines come up like this, but the longitude runs this way. And you have to be within a half a degree of correct longitude. That'd be enough to show you where the rocks are, so to speak. All right? And they would offer an award of that 20,000 pounds. And if you account for inflation, and in fact it's in pounds, that it would amount to about $12 million today. So that would be something worth working on. That would be something worth pursuing. It'd be like, what are these reality shows like Survivor and what's that one where they travel all over the world like crazy people? Amazing Race. That'd be that sort of thing. I think an Amazing Race, they all know where they're going, okay? And something gets them there. If they had to use longitude and latitude, they'd never win. Two gentlemen. I'll go through it. There's a lot of people who went for the prize, a lot of cuckoos. There are people who even suggested stationing ships across to like Barbados at 100-mile intervals and firing a cannon every hour so that you couldn't be any outside of earshot of a cannon. And there you go. I mean, sooner or later, hopefully they wouldn't use cannonballs, real cannonballs. They would put a dent in the transport of goods from east to west. But anyway, that was a crazy idea. Somebody else had a perpetual motion machine. And there were all these things. Only two people, in the end, came up with a reasonable solution. One was John Harrison, and the other was Neville Maskelyne. Now, Maskelyne was an astronomer. He was the astronomer royal of the Greenwich Observatory. That's big time, okay? They're in charge of looking at the heavens. Harrison, I don't mean to demean him, he's a carpenter. Now, you know what the end's going to be, don't you? You know how this is going to come out, don't you? You know that this carpenter of Lincolnshire and the royal astronomer of Greenwich, you know this is all going to end. You realize it right now. Well, let's see. Since you know the end of the story, let's see how we get to it. And you'll notice that Maskelyne was quite a bit younger then. They were contemporaries, but he was kind of the young punk, so to speak, to Harrison. The longitude solution. It's going to require a clock, okay? So we have a clock. Water clock. Somebody mentioned water clock earlier. Now, water clocks were really quite accurate. They go back to 1200, 1100 AD, even sooner. It's just a matter of having a funnel here, collect water, and keep the water at the same level in the funnel by a water source. And then there's a little device here that allowed the water to leak through and drip. So I go drip, drip, drip. They'd keep you awake at night. Wouldn't be a good clock radio, all right? So this would, and then a plunger here would turn a gear, which would turn an indicator indicating the hour of the day. And they worked pretty good. They were around for hundreds of years. And then the sundial's been around for a long time too. The sundial is really a neat device. Now, the timekeeping element in a water clock is what? The timekeeping element is you depend upon the water doing what? Dripping. How though? Constant. At an even interval. You don't want to go drip, 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 drip. You don't want that. That's bad clock, all right? The sundial, what's the timekeeping element of the sundial? Could be the what? Now you say the sun, but what's causing the sun to shine on the sundial so that the shadow moves? What's really causing that? The rotation of the Earth. You're counting on the fact that the Earth's rotation is constant. It doesn't change much. And it's true. The Earth's rotation is remarkably constant, but it is slowing down because the moon is a real drag. Seriously. So we have to add a couple of seconds every now and then they're called leap seconds, to adjust the clock to keep up with the actual rotation of the Earth. So the Earth is slowing down, but not by a lot. Then you have the good old pendulum clock. I have one over here. I brought it with me. And it's ticking away. Is it right? No, it's slow. Okay. So the way to fix that, I'll show you how to fix it. Galileo, very smart man, was observing while he was sitting in a chapel one day in the cathedral. He's looking at the chandeliers. He noticed the wind coming through the windows was causing the chandelier to swing ever so gently. And he noticed that the period of swing was constant. It was a nice, simple harmonic motion. And the way he was able to to convince himself of that is because he uses pulse. And if you didn't get too excited, your pulse rate stays pretty much constant. Unless you have that atrial fibrillation, then you're not going to be worried about pendulums swinging back and forth. Okay? So you have a nice steady pulse of 60 pulses. Mine's about 60 a minute, so 1 per second. Okay? If I'm sitting around doing nothing, it goes down to about 40. So if I were just doing something, like now, it'd be about 1 second. I could see that this pendulum keeps a constant swing. I also noticed, and he didn't really, he observes this, I'm sure, that if you shorten the length of the string, what happens to the period of swing? It's smaller. It goes faster. And so what I have to do with that clock over there is on the pendulum, I have to well, it's going slow, so I have to shorten a little bit. If I shorten the pendulum a little bit, the clock goes a little faster. It keeps up with the one on the wall over there, which keeps up with the one in Greenwich. The pendulum. Now, the question is, in order for this to be a clock, all right, let's put it down low again here. In order for this to be a clock, you've got to have someone count the swings to keep track of time passing, all right? So as time passing, 1, 2, that would be a drag after a while. You wouldn't want to do that. So you have to have a mechanism that takes the swing of this, takes the simple harmonic motion of this pendulum swing and converts it into rotational motion, which can turn a minute hand, an hour hand, a second hand, and you then have a clock. And in order to do that, you need a device which came up in the 16th century, 17th century, and it's called an escapement mechanism. Even the machines fall asleep on you. Okay. Now, these are mechanical devices, all right? This is an astronomical observation. That is the moon. Those are stars. Judging the position of the moon with the stars is like a big celestial clock. Interpreting it is a bugger. Okay, and I'll get into that. The sundial, I borrowed this sundial from my son in Folsom, and this sundial from my nephew in San Diego. You notice the difference in the style? This one is pointed up higher. This one's not pointed up as high. And the reason for that is the angle of the style, the cast of shadow, is determined exactly by the latitude it's at. So if I wanted to follow up my nephew, I'd give him my son's sundial. If I want to screw up Greg, I'd give him Jeff's sundial and switch them around. Then the sundial wouldn't read the right time. But everybody looks at a sundial now and say it doesn't give the right time now. You know, say a clock that stops is right 2 times a day. Sundial isn't even right 2 times a day. And the reason for that is that it's tracking the sun. And if you look at this monument sundial, it's a beautiful picture. This picture took an entire year to make. And what this photographer did, set the camera up here and took a picture at exactly 10 o'clock every day. Next day, snap. Day after that, snap. Or maybe 5 days later, because there aren't 365 suns up there. Maybe every 5 days. And in the time he took the picture, was the mean solar time, was the Greenwich time, was the Pacific Standard Time, whatever. It was a standard time. It was a fixed time, constant, day after day, exactly the same interval. But notice the sun. It's on, let's say, this is May. On May, it got a little higher at 10 o'clock. And over here in July and August, and get over here, it was a little lower in that month, at that time. It speeds up and slows down. And the reason it does that is because as we spin on our axis, we go around the sun in an orbit that speeds up and slows down. Because when we're closer to the sun, we go faster. When we're farther from the sun, we go slower. And we're also tilted. As we tilt, the sun has to travel up, like over here, has to travel from here up on the what they call the ecliptic. In the wintertime, it travels down here. So it goes up and down, faster and slower. So that's why you get this figure 8. If you want to see one, just come over and look at the globe. And in the Pacific Ocean, right here, is the analemma. And you can pick a date and figure out, when you go out and look at the sundial on the wall out here, how fast or how slow it should be. That's what determines it right there. So if you ever look at a sundial, don't get too harsh with the sundial. It's not the sundial's fault. If it reads a little ahead of your clock, then it's probably because of the equation of time. Or another reason, they didn't correct it for longitude. Okay? So I showed you the pendulum and the timekeeping with the pendulum and timekeeping elements. An element of timekeeping is how the time passes, the dripping of the water clock, the rotation of the earth, the swinging of a pendulum. I didn't mention to you, though, how you can convert that simple harmonic motion into rotational motion. And that's, as Joe said earlier, is why a clock goes tick-tock, all right? And right here, I saw this on YouTube. And I could have showed you the YouTube, but I said, no, I'm going to build it, all right? And so what you have here is a device that represents what is known as an escapement mechanism, okay? Let's see if I got this right here. There we go. Now, if I let this weight go, put these things out here like this, it's like a metronome. You've seen a metronome. And if I put these out here, that's kind of like, what is slow? Largo? Largo? Okay, this is kind of largo here. Okay? The tick-tock from the hanging weight. Okay? So that the weight is supplying energy to the wheel, which is interrupted by the paddle. And then as it's interrupted, this simple harmonic motion is allowed to persist, and hence you have the clock. This wheel right here is turning. I could hook that up to a gear, a little belt, a little, do something with it, make a second hand, then make a hour hand, okay? That's how it works. If you want it to go faster, presto, right? Presto. Presto is in here, and let it go. Okay? Simple as that. I thought you'd like that. Okay. Now, the more sophisticated version of this looks like this. This was an escapement mechanism, one of many. The one on the right was designed by John Harrison. Again, he was a carpenter, but he was very, very precision carpenter. He was not really a carpenter. He was a skilled craftsman, or even further than that, So he's a carpenter. You get that. You might think, well, he maybe builds houses, which is fine. But to do precision building, this is what Harrison was able to do. He's a very smart guy, self-taught, learned a lot, didn't go to school, any colleges where he would have learned all of that. He taught himself those things. These two mechanisms right here, this wheel, you imagine it's the wheel in that thing I just showed you. And it's got weights hanging from it, like in a grandfather clock. The weights turn that wheel, but not too fast, because this thing gets in the way. That's the pendulum. What keeps the pendulum going? The weight. So every time the escapement hits, notice that it's pushed off. See how it's pushed off? It gives the pendulum a little tug every time, and that pendulum keeps going on and on and on, as long as the weights are up enough so that it provides energy to the clock. So that's basically how that works. Now, let me ask you this. Pendulum clock, like the one over there. Water clock. Sundial. Which one of those would you take on a ship? None of them. They're worthless on a ship. The sundial, is the ship always going to be headed so this dial's pointing north? No. Are you always going to be at the latitude for the sundial? No. If you have a pendulum that's swinging back and forth, the ship is pitching in a big swell, is the pendulum going to behave properly? No. Okay, water clock, well, you got a lot of water around you. That's a cool part. But the clock's going like this, and the drip rate's changing. So consequently, none of those are. So you had to build a mechanism that would actually keep up with or counteract the motions of the ship. So this device right here, encased, might do the job, but what he did is he built a mechanism that looks like this, and it would go like this. And no matter how the ship pitched and rolled, that would not interfere with the mechanism that kept the time. These are Harrison's 4 clocks. He built them, some of the gearwork, out of wood. And the wood he used is called lignum vitae. What's that mean, Ryan? Hardwood. Hardwood. Not wood of life or anything. Lignum vitae. And this wood right here has a characteristic that it lubricates itself. So all the bearings in the clock had this wood in them. Another characteristic of the wood is that nobody ever believes me. You know, if I told you this wood wouldn't float, you know, this wood floats. There it is right there, okay? That's rosewood, very hard wood. There it is. It's sunk. So are you happy now? All right. There it is.
Do that again.
Do that again?
There. We just need a bigger sample.
So anyway, that wood was used to cut into gears. It was used mainly for bearings. Because that's true. It stayed pretty much intact, and I have something that fits right into that in just a minute. I was going to start my own cooking show. Okay. But these 4 clocks, H1, H2, H for Harrison, the first one worked pretty well. He went on a trip from, I think, Lisbon, from Portsmouth to Lisbon, took the clock, and Harrison got sick as a dog, seasick. He finally got the clock to work, and it worked within the boundaries of the prize. So technically, he should have won. But he kind of shot himself in the foot, because when it went back to the Board of Longitude, these are the referees. These are the people trying to determine whether you should get the prize or not, because it's a big chunk of money. He said, no, it's not working well enough. I'm going to improve upon it. So they gave him money. It's probably, it was the first incident in the world of R&D grants, research and development. He gave him about 200 pounds. And he built a clock 2 and, try that again, Dick, go backward. There you go. He built clocks 2 and 3, this one and this one. This one didn't work very well, and this one never got on board a ship. It just kept going down. And look at the time span here. 1728, 1740, 1760. He's got 30 years of building clocks to get one that would hit the mark, that would win him that 20,000 pounds. And so far, only Scott out of it. He got half the prize, and I think when he got to H4. With H4, he went to a clockmaker, one that built a little clock. He designed the clock. Harrison designed the clock. They built it. H4. These clocks weigh about 40 pounds, by the way, 40 to 50 pounds. They're heavy. They're not, you wouldn't put them on your wrist, that's for sure. This clock, it looks like a pocket watch, but here's a pocket watch right here. This clock, the Harrison H4, is about that big around. It weighs about 5 pounds. Okay? But it worked well. It went on a couple of expeditions. It went over to Barbados, went over to that area, and it came back, and it kept within the mark. But for some reason, the Board of Longitude, who was then presided over by Maskelyne, they wouldn't give him any leeway. It says, no, now you've got to be able to reproduce it. You could build one, but now you got to build more. So he built the H5 and built more of them, but they kept really giving him a rough time and pushing him around. And by the way, with a clock, even when you take a clock and set it for the Greenwich time when you leave port. In fact, I forgot to show you this, but on the top of the Greenwich Observatory, there's this big red ball. And what that ball does, at exactly 1 o'clock or a few minutes before, the ball rises. And at exactly 1 o'clock, it drops. So everybody in the harbor can see it, set their clock. All right? They do it differently now, of course. But once they get to wherever they're going, once they're a sail and they get out into the ocean, they have this clock, this Harrison clock as it is. It's got the exact time at Greenwich. And so now they look using the sextant here, this device. This was developed in the 1700s, right around the time that the prize was being awarded. And this device is able to measure the distance between, let's say, the sun and the horizon. And I invite you to come up and check it out. You look through this end, and you take this object that's in the mirror, through the glass here, as to say the horizon, and then the sun reflects off of it, and you have a sun filter to protect your eyes. What you do is you move this until the sun comes down to the horizon. When the sun just touches the horizon, you read the angle, and you can read it to a fraction of a degree. In fact, a half of a minute of arc, which is the 60th of a degree. Then you get the elevation of the sun. When you find the sun that's highest in the sky, you know that's noon. And if you know it's noon where your ship is, and it's, let's say, 2 p.m. in Greenwich, you're 2 hours behind it, right? Which is exactly 15 degrees an hour, is what the Earth turns, 30 degrees. So you're 30 degrees west longitude. And you know your elevation, or you know your latitude by observing the sun itself, how high it gets, or observing the North Star. So there you have it. You have longitude and latitude. Now, how can you do this? Maskelyne would ask, well, how can you do this without a clock? I got an idea, all right? Galileo, leave it to Galileo, okay? He did not invent the telescope. He found out about these optical arrangements he could make with lenses and look not at the birds, at the trees, or at people. He could look at the sky. He look up in the sky and discover the craters of the moon, found by projecting the image of the sun on a piece of paper, the spots on the sun. But one particularly good observation he made, a very, very, very profound observation, any one of those would have given him a Nobel Prize today, were the moons of Jupiter. The moons of Jupiter move around Jupiter like a clock. They have a certain tempo, they have a certain rhythm, all right? And if you look over here, you see Chris brought in, thank you, Chris, for bringing this ship's telescope in. Can you imagine being on the deck of a ship, pitching and rolling, you know, looking at Jupiter? You know, that. You don't think it'll work, do you? Chances are it won't, and it didn't, okay? But in theory, okay, these guys are heavy theory guys now. You could use a telescope like this and get a little bigger field, maybe a little better view of it. But this whole idea, let me show you right here. This picture on the left is a sequence of pictures of Jupiter and the moons. And look at the harmony here. Look at the pattern, how it swings down like this. Look at the pattern of the almanac over here. It looks like an hourglass. Isn't that appropriate? Okay? Everything that's happening on here happens in a periodic manner. It has harmony. It's repetitive in equal intervals. It doesn't change. It doesn't go crazy and then slow way down. So it became, I must have got so excited I pushed the button. So these images of Jupiter show you the change in the positions of the moon. Now, this book right here, I took a bunch of them off the shelf. Hope you don't mind, Sabrina, okay? This book has the satellites of Jupiter. It's called the Astronomical Almanac. This is what no nerd can do without, okay? Right here. So right here, you have the positions of the moons of Jupiter. It tells you when the moon, exactly the time the moon goes behind the planet. So imagine this. These are all set for which time? Greenwich time, okay? So here's your clock. You look at the planet Jupiter. You could be out in the middle of the Pacific Ocean, okay, 100 degrees in longitude away from Greenwich. Look at the moons of Jupiter. It's going to be doing the same thing it's doing in Greenwich. So when the astronomers at Greenwich collected all the data, tons and tons and tons of it, it just make you go to sleep, okay? But it was all there, and you look at it, and you say, I'm looking at the moon of Jupiter. The moon Callisto is this far. The moon Io is this far. The moon Europa is way over here. That's the exact pattern they see in Greenwich when it is 2 in the morning. And here it is 8 in the evening. So the difference in the time between your local time that you determine with your sextant and the time in Greenwich, the difference gives you what again? The longitude, right. What's the latitude? Well, go out and look at Polaris. That's the latitude. Simple as that. So you got it. So this is an astronomical solution. Now, it didn't work very well because you couldn't look at the planet Jupiter. It's a very small object. Galileo barely detected the moons. So there's another way. Right over here, it's called the,
Also not out all the time.
No, it's not. And that's a pretty good reason for this one right here, not using this one. This is called lunars. And lunars is taking the moon's position and measuring it relative to the sun. And again, you use the sextant to do that, but you don't need a clock. Because what's happening is you're looking at the clock. This is the clock. The time in Greenwich that the moon would be here relative to this star and at this altitude, you look it up in the tables that they created, the tons and tons of tables. You look it up in the tables, and by that measurement with the sextant, you can determine what time it is in Greenwich. See, all you ever want to do is what time is it in Greenwich? And then you determine by using this instrument again, elevation of certain stars, what time it is where you are. So one, as long as you have a moon and a sun. Sometimes you do it during the day. Now, what if it's not clear? Okay, it's not clear. It suddenly gets foggy out, but you can get a fix on a star to get an idea of your latitude. So if you get your latitude, you just go and sit down, kick back, have some ale, and look at your what? You look at your chronometer. And by the way, the term chronometer didn't come around until about the 1700s. It was kind of invented. Somebody was writing a poem, and chronometer kind of rhymed with something else. So there you have it, chronometer. So there you have it. So, but it worked. It worked very well. They got within the limit of the prize. They got within 2 minutes of arc, half a degree of arc. It all worked, and there was this, who's going to get the money? Well, Harrison had been working on this for, like I say, 30 years, and finally the seaman, this, by the way, if anybody wants to know how to determine longitude and latitude by the Lunar's method, be my guest. It's right here, okay? People today, amateur navigators, will use this. If you can master this, you'll know everything there is to know about navigation. But I don't want to. So when you think about it, using the moon and the sun depends upon a clear sky and an availability of the moon and the sun. So you had to go kind of rogue for a while. An interesting thing is that Maskelyne said that we can use Harrison's clock when it's cloudy. So they did depend on it. So it became a case of mechanical clock versus astronomy. Now, one of the greatest minds of all time, Sir Isaac Newton. This is what he came up with. He says, longitude at sea is not to be found by clockwork. He didn't trust the black box. He says, nothing but astronomy is sufficient for the purpose. So he sided with Maskelyne. He sided with the astronomers who would look at the stars at night using instruments, okay, using machines, finding the angles between the moon and those stars and the sun, and determining longitude that way. And it can be done that way. It can be done fairly accurately that way. But it takes, on the average, 4 hours to do a shoot to determine a longitude using a lunar method. Clock method, sextant, 10 minutes. Okay? I've never done it. I'm not a navigator. I'd like to take a course in learning how to use that sextant. I'm just speaking to you for what I read. There he is. He still didn't get his way. They were still holding out on him. So he went to the top. Guess who he went to see? Good old George III. Okay? And George III happened to be a kind of guy that liked entrepreneurship. He liked this. He was kind of a science buff. He had a lot of books on astronomy, a lot of books on various elements of science. And he granted an audience with Harrison. Harrison told him what happened, and he was outraged. He says, they should have paid you years ago. And so somehow, John Harrison got awarded almost the rest of the money because he'd already gotten 10,000 pounds. This might have been the amount of money he got minus all the grants he got, for doing the clock. So finally, in the end, he was near death. He died at 83 in 1776. And by the way, in 1776, this guy had other things on his mind. You know what I mean? Okay, let me go back. King George was probably thinking about what's going on. There's a tea party going on. But Harrison was able to win him over and get the rest of his money. What happened to lunars? They finally went out in the early 1800s. They stopped using them. They're too hard. Clocks were manufactured. Let me go back here. Sorry about that. That clock right there, H5, he had assistants. In fact, one of the stipulations, they changed the rules, by the way. The Board of Longitude said, okay, that clock works. It's well within the specifications of the longitude prize, but you got to make them yourself. You got to build them. And he said, oh, like that. That's when he went to the king. King said, no, that's not right. So he had a fellow help him with the clocks. I have a hard time remembering stuff. Larkham Kendall, in fact, the K1, K2 were the Kendall clocks. And they were all designed by Harrison, but nevertheless, he had help with the actual intricacies in building the clock. Being 80 years old, or even 75 years old, so that little stuff is kind of hard to do. Okay, so we talked about King George, and then finally, in Harrison's credit, he got the last word, by the way, even after he died. This particular church, or the steeple right here in Brocklesby Park, he built the clock for this in 1720. Made out of wood. A lot of the gears were wood. That clock is still running today, almost 300 years later. One maintenance call, that period of time. That clock keeps good time. That was back then. But even now, as of last spring, Harrison had a design that he claimed would give a clock the accuracy of losing less than 1 second in 100 days. And they all laughed at him. They said, that's incredible. He couldn't build the clock, but he had the design. And recently, this gentleman, artist Martin Burgess, in the late 20th century, just recently, tried to build a clock. I think it was in 75. He succeeded, and finally it was demonstrated in April of this year to actually lose less than 1 second in 100 days. And that clock was designed by John Harrison. And it is now in the Guinness Book of World Records for the most accurate pendulum, mechanical pendulum clock that exists. Of course, now we talk about atomic clocks, talk about a clock that loses a second in 1,000,000 years. Do you really worry about that? Okay. No, you don't. Okay. But anyway, finally Harrison passed away. Wealthy guy. He was a wealthy man for the days. But he is buried in Westminster Abbey. Maskelyne is not there. He's in a church cemetery somewhere. He's buried in the same room as Sir Isaac Newton, Charles Darwin, and a number of course, a lot of people. Have you ever been?
Did Maskelyne get any money?
Well, he got prestige, being the Astronomer Royal and the head of the Longitude Committee, which was disbanded in 1828, but that was before he died.
But nothing for this.
He might have gotten something, you know. You know what, Brian? I don't know the answer to that.
That's all right.
But basically, that's what it is. So, my hour is almost up here. Let's see, and I'm going to give you some time. And right here is a question. This is a quiz. We'll take 1 minute, a quiz. Okay? Here is the Greenwich time. It's 2 o'clock, and it's p.m. And they had to keep track of that, by the way. They didn't have the 24-hour clock. They kept track of whether it was a.m. or p.m. They had a calendar in the same room. They kept marking off the days. They knew what day it was. It's 2 o'clock. Sextant. Determined the latitude was 20 degrees. The local time, 3:30 in the morning. 3:30 in the morning. Here in Greenwich, it was 2 in the afternoon. Where are you? Okay? Too hard. Now, Greenwich Meridian time, 2 p.m. is 14 hours, 1,400 hours. You add 2 hours to the 12. Sextant time, 3:30, 10 hours and 30-minute difference, 15 degrees per hour. So it's about 157.5 degrees west longitude you are at, 20 degrees north. Where are you? Michelle, you're going there next week.
Go back to the
Push the button again.
What did I do? Gee, did I do something again? What did I do?
hit the
Push
button.
back to the end.
You got too excited.
Oh, sorry. There we go.
There you go.
See, I don't even know what I'm doing. All right. So I'm looking over here. What was the? Tell me the longitude again. 157 degrees west. Okay. Okay. There's 130, 140, 157 degrees west. That's right about here. It's all in this meridian. How many degrees north?
20.
10, 20. Right there. Looks like what?
Big Island?
Boy, you're really getting down to the nitty-gritty, aren't you? That's not, Hawaii is not good enough for you. It's the big island in Hawaii, and that's where you'd be, okay? Well, what did you do? You used the sextant to determine your position as far as latitude. You used your handy-dandy Harrison clock for longitude, and that's all there is to it. And by the way, I'll leave you with this message of this great intellectual thinker, okay? Yogi Berra. When asked, what time is it? His answer was, do you mean right now? Okay. Thank you, folks. You're free to get up and look around and do stuff. And
You didn't.
oh, yeah. Thanks, Joe.
There's one thing that you skipped over real quickly because you assume that everybody knows this.
Yeah,
This Earth is spinning,
yeah.
and you said 15 minutes in an hour, 15 degrees
15,
in an
yeah,
hour
right,
type of
right,
thing.
right.
So this Earth is spinning how fast? You're standing right here. How long does it take to go all the way around?
24.
24 hours. If you're standing right at the North Pole, how long does it take to go all the way around?
4 hours.
Interesting, right? So which one has to travel farther?
Equator.
So if you're on the equator right here, which is the fattest part of the globe,
Right, right.
roughly, you're going around the Earth in 24 hours. How fast are you going?
Well, put up the numbers. The 24,000 miles roughly in 24 hours, about what, 1,000 miles an hour.
That's why you don't get pictures of people at the equator. They're all being blown off right at the equator.
I knew it was coming. I knew that you couldn't hold it for more than a minute, could you?
But if you're going 360 degrees every 24 hours, if you divide 360 by 24, you get 15 degrees.
Per hour,
Every
right.
hour.
That's how I came up with the 15 degrees per hour. Sorry. Thanks, Joe. Another thing I forgot to show you was the concept of running a rum line. That's not R-U-M, that's R-H-U-M-B, okay? And a rum line is where the explorer maintains the same latitude as they go across, which is what people like Columbus, Vasco da Gama, and Sir Francis Drake, they all found a latitude they liked and stayed at it. And all they had to do is keep the Star Polaris at, let's say, 40 degrees altitude all the way. Well, if you run a rum line, you're going a lot further. You're losing a lot of gas. In fact, it's an interesting statistic that if you were to take the city of New York right here, and I laid this out along a parallel latitude all the way to I don't have to do it. We did it earlier. Trust me, Joe and I did it earlier. And run it all the way over here to Japan, northern Japan. I got about that much, that's that far right there from New York to northern Japan along a latitude parallel. Now, if I take this string and put the end of it in Japan and stretch it across the globe to New York City, then I get there. You see the knot? See the difference? That's how much further the plane would have to travel. Another couple thousand miles, another 4 hours in that aluminum fuselage with peanuts, okay, for that period of time. So that's why when you leave an airport and you see yourself flying over Greenland, so why are we going to Greenland? It's because you're traveling along a great circle. If you want to experience a great circle here as you're driving down the freeway, the way you would experience it is just take the wheel, hold on to it, and don't turn it, and keep going. Okay, you're running into difficulties, all right? But that car is going along a great circle, all right? Okay, well, get up and look around if you have questions. And I have a sundial over here, by the way. I presented it to Sabrina earlier. This sundial does not tell you the time of day. This is an Italian sundial. No cracks, Joe. Italian sundial. And the shadow, let me show you, right here. Here's the sun. Okay, you see that shadow I'm casting right there? That could be the sun. At the shadow, the end of the shadow is right here. What that means, there's between 2 and 3 hours until sunset. This tells you when the sun's going to set. It doesn't tell you what time it is. It tells you how many hours is left in the solar lit day. You know where this was one of these is posted? Is on an airport hangar. And the reason it's there is because when pilots go up and they're not checked out for evening or night flights, they know that they have so many hours they can fly. And that's what this device is. I'd like to get one put out on the library, really nicely done. I was going to ask the art department to design the radials here, the lines, so that as you walk by, you can see by the end of the shadow how many hours it'll be to sunset. If you care, all right? But it's just an interesting thing. Instead of reading a sundial, this one's never wrong. This one's always right, because what you're doing is you're looking at the motion of the sun and not your clock. So it tells you what the sun's doing. It's been a lot of fun being here. And if you have a few minutes, you want to come up and chit-chat, I'd be happy to talk to you. If you're willing to talk to me.
No questions? Come on up.
Good question.
Yeah,
Why does the Earth have a tilt, an axis, 17 degrees?
that's a good question. Some planets don't. And it's all in the formation, how it might have been impacted with all the debris that was in the early solar system. Yeah, yeah, yeah. And there's so much mass, there's so much inertia, it keeps tilted that way. But the interesting thing about the Earth, though, is that as it's tilted, it's like a top, a spinning top. If you spin a top, you know how a top goes like this? It's precession. And the reason it's precessing is because the gravity of the sun is trying to get the equator's plane in the same plane as the direction of gravity. And it won't do it. Instead, it goes like this. It's reluctant. Yeah, it's wobbly. Yeah.
That's I wonder we don't fall off. You're right, as you're saying.
Uh,
Then old by the way, they all wear those metal shoes that stick down.
I can't keep a serious conversation going here.
Somebody got Yogi Berra up there.
Okay, well, that actually did it. I broke the ice with that one.
Thank you, Dick.
You're very welcome, Phil. It's
Excellent.
always a pleasure.
Thanks for coming, folks.